Before we finish up the chapter and move on to two-dimensional motion, I do want to make sure we revisit graphing. Graphing is incredibly important to be able to understand how these quantities relate on a graph. So, for example, let's say that I throw up. Nope, I throw something up. Still doesn't sound right. But anyway, maybe I need to figure out what I'm going to throw up. Let's just throw our physics book up. I don't know. It doesn't matter. I couldn't think of anything creative, but throw our physics book up with some initial velocity in the upward direction. And we know that it's going to go up, 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 and then it's going to stop at the top, turn around, and come back down. If it's one-dimensional motion, it's going to come back down along the line, which I threw it. I just drew it a little bit offset just to show goes up and then comes down. Okay. So let's go ahead and graph the position, velocity, and acceleration of the book as it goes up and comes back down. So first thing we have to do is, in order to graph it, we got to define our positive direction. So do you want to call the up direction positive or the down direction positive? Because that's going to determine what our graphs look like. I don't know. I wish you were here to tell me which direction you want to be positive. But let's go ahead and call up the positive direction. Do we want to call it X or Y? It doesn't matter at all. I'm going to call it Y just to get used to calling vertical directions Y. We don't have to, but I am. So I'm going to graph Y versus T, position versus time, in one dimension, right? This is just Y in one dimension. And so then think about what happens to the position of this book as it goes up. So first of all, we got to figure out what our origin is. We haven't really thought about that, but really our origin is where we start typically. It doesn't have to be, but we're going to call that y equals 0, right? And so we're going to say, oh, it's going to go up the y-axis. So we'll call this y equals 0. So it starts at y equals 0. So it starts at y equals 0 at t equals 0. We just say we start our stopwatch when we throw it upwards. Now, what does the y versus t curve look like? Think about what happens to the position as it goes up. The position as it goes up, the position increases as it goes up. The position gets bigger, but the speed slows down. So for every increment of time, we're covering less and less distance. So in the first increment of time, we cover a certain amount of distance. In the next increment of time, we cover less distance. In the next increment of time, we cover less distance. So the y looks like this, right? And what happens is eventually we get up to our maximum height, right? Y maximum, and it turns around and comes back down. So it's got to come back down like that. So it's exaggerated perhaps, maybe it's not in the t direction, but what kind of shape is that? What's that shape called? Right? We can actually write an equation for this shape, right? It's delta y equals 1/2 at squared plus v0t, right? That is a quadratic equation, or it's a graph of a parabola. If we graph delta y versus t, we get a parabola. If you didn't know that, you can go back and review what a parabola is, but this is indeed a parabola. Okay. All right, so I don't mean to be drawing over it. So on the way up, parabolic. On the way down, parabolic. The whole thing, parabola. Okay, so what about v versus t? Let's go ahead and do the same thing for velocity, not speed. Velocity in the y direction, v sub y, versus t. There is no x direction. We didn't really have to put a subscript there, but velocity in the y direction. Well, now think about what's its initial velocity. So up is positive. The initial velocity, where does it have its highest velocity? It has highest velocity at the beginning. It slows down after that, right? So the initial velocity is right up here. This is v0. I can mark that. Okay. This is v0. And then as it goes up, as the book goes up, it slows down. But how does it slow down? Does it slow down quadratically? like the position? Does it slow down constantly? Well, remember that the slope of the v versus t curve is acceleration. The slope of the v versus t curve is acceleration, and the acceleration is constant. So this slope better be constant. Now, just to be really careful, I do want to point out that at the top of the curve, if we make these the same times, at the top of the curve, what's the velocity? That's another point we know. At the top of the curve, the velocity is 0 in one dimension. In one dimension, it's 0. So the graph of the velocity versus time must be a straight line, because the slope of that straight line had better be the acceleration. But what about the second half of the curve, right? The velocity stops. And then what happens? It gets bigger again, right? It gets bigger again, but the velocity on this side, right, if we look at the book here, the velocity is pointing in the negative direction, right? It's pointing in the negative direction, so the velocity is getting bigger in the negative direction. And it should end up being that when it comes back down to the ground, it's going to have v0, but in the negative direction. Okay, so there's your graph of velocity versus time. And again, real quick, the slope, no, I guess I wasn't so quick. The slope of v versus t is a. A equals a constant. So that better be the slope. The slope of that is a. Okay. But also remember that the slope of y versus t is v. So you can see, if you follow along the v curve, right, it's the velocity is, let's just look at t equals 0 right here. The velocity is the highest. So the slope of the y versus t curve is the highest. I'm going to draw a tangent line. The slope is the highest. As we go down, the velocity gets smaller. So here, the slope better be smaller. So here, at the same point on the y versus t curve, the slope is smaller. Tangent line is smaller, right? The slope of the tangent line is smaller. Here at 0, right, when it gets to 0, the velocity is 0. That means the slope of y versus t must be 0. Whoops, that was the wrong color. The slope of y versus t is 0. Okay, so if the velocity is 0, then the slope of y versus t is 0. Right? Because so the parabola, if y versus t, if the slope of y versus t is v, and v is getting smaller, then the slope better get smaller. But then as v passes through the axis, v is getting bigger in the negative direction, and the slope is getting bigger in the negative direction, right? The slope gets bigger, bigger, bigger. Okay. All right. And what does the acceleration versus time look like? Okay, so we're going to draw a graph of acceleration versus time. Now, I'm just going to cheat and put my axis up here because I know what it's going to look like. Acceleration versus time. Because what is the slope of v versus t? The slope of v versus t is a. I chose up as positive. Either one of those. These are two separate ways to look at this. The acceleration is negative. The acceleration is negative 9.8, and it's constant. So the acceleration is negative 9.8, and it's constant. So that's graph of a versus t. It should be a line with slope of 0 because it's a constant. The fact that the slope of v versus t is a, and the fact that the slope of v versus t is a constant, means that a is a constant and it doesn't change. Okay, I've said that enough times. There's your graphs of position, velocity, and time. Ooh, what about speed? Speed, something different, right? When the book goes up, it slows down. When it comes down, it speeds up. So what would the speed graph look like? I'm just going to put the speed graph on top of the velocity graph. The speed is the same as the velocity on the way up. It slows down, slows down, slows down, slows down. But on the way down, speeds up, speeds up, speeds up, speeds up. So there's the speed versus time. It's a V, right? The speed versus time. Okay. So these are graphs for constant acceleration in one dimension. You should understand these graphs. Constant acceleration in one dimension. Let's just compare them to the graphs of constant velocity in one dimension. So constant velocity is just a special case of constant acceleration, right? So constant velocity, whoops, I'm doing a thick line, that's all right. So let's just say this is y versus t, b versus t, and a versus t. Okay. Right at the bottom, if we're traveling at constant velocity, what is the acceleration? Constant velocity, you're not changing velocity, so your acceleration is 0. So it's a graph that goes along the x-axis, along the, I guess, at a equals 0. Okay. Constant velocity, what does a constant velocity graph look like? V versus t. What is constant? If I'm traveling at constant velocity, it's not a falling body, right? Because it can't travel at constant velocity. It's a car traveling at a constant velocity of 55 miles an hour. Well, constant velocity, whoa, okay. Constant velocity, there, that's constant velocity. So these are graphs of constant velocity. Acceleration 0, velocity is constant, and then that means that the slope of position versus time must be constant. The slope of position versus time must be constant. It doesn't mean it's y equals t. It doesn't mean, y equals x, y equals t. It could be any graph like this, right? I'm just drawing a bunch of them just to show it doesn't matter which one it is, but it's one of those. Constant velocity. Any one of those, depending on the slope, right? This is the slope of y versus t.